I'll be using the rotational period of the Earth several times, which is 23 hours and 56 minutes rounded. Notice that's not 24 hours, and here's the reason why. I put, let's say, my Smurf here in Berlin, Germany, and the Earth rotates, and then 23 hours and 56 minutes, the Smurf is back to the same point here in Berlin, Germany. But at the same time, the Earth has also orbited the Sun a little bit, approximately 1 day, and that is approximately 1 degree, so it orbits just a little bit, and so it needs to rotate just a little bit more in order to be in the same position relative to the Sun. That's the extra 4 minutes. And so, yes, 23 hours, 56 minutes for one rotation, plus an extra 4 minutes to make the 24 hours for 1 day, again because the Earth also orbit a little bit. So I'll be using the rotational period, and I will either use the true 23 hours 56 minutes, or I will round it to 24 hours. Alright, I'm going to turn the sun actually off. I don't need it any longer, and I'm going to turn the lights on here so we can actually look at gravity better. So the acceleration due to gravity on Earth should be 9.83 all the way everywhere on Earth. It ought to be, but it's not because the Earth is rotating. By the way, it's kind of nice to sit down in this chair as gravity is holding me down here to the air, and I don't have to stand. Either way, gravity is actually holding me down. 9.82, by the way, in Alaska, 9.82 meters per second squared. Okay, so 9.83 everywhere. However, the Earth is rotating, and two things are happening. One of them is that as the Earth rotates everywhere in the rounded 24 hours, or 23 hours 56 minutes, a little bit more exact, so the rotational speed is the same everywhere, but the tangential speed is not, because at the equator it has to make 40,000 kilometers or 25,000 miles roughly in 24 hours, while at the latitude of Berlin or Alaska, the two are actually not that much different, 53 degrees latitude versus 60 degrees latitude. Notice that the circumference is much less. In fact, at 60 degrees southern Alaska, it's actually only 20,000 kilometers, so which is roughly 12,000 miles. So it makes much less distance in the same amount of time in the 24 hours, which means the tangential speed, and therefore the inertia, is much less here at this latitude than it is here at the equator. So that tangential speed means that as there is more inertia here, some of the gravity, the 9.83, is taken up to keep the Smurf to Earth, pulling him inward. And so when you make a measurement of the 9.3, you're not going to come up with 9.3 because some of it is already taken up by the centripetal force in order to pull it toward the Earth. And that comes out then here at the equator. It actually reduces it to about 9.78. Here in Alaska, it reduces it to 9.82. Again, because of the smaller circumference. At the North Pole, where it also rotates in 24 hours roughly, but there's no circumference there, so you don't have that tangential speed there and no necessary centripetal force to pull the Smurf or any person inward. The other reason is also caused by the rotational speed. The Earth is not a complete solid. There's actually a liquid outer core in there, and the mantle in between the crust and the core is somewhat able to stretch. So with the tangential speed of the Earth here being larger at the equator, the tangential speed, the inertia, actually, so to say, tries to push the material forward instead of inward, and so you get that bulge here, that what's called the equatorial bulge. So here, actually, when I describe this as 40,000 kilometers, that's actually 40,023 kilometers, while going over the poles it's 40,000 kilometers, which means that the equator is a little bit further away and the pole is a little bit closer towards the Earth center, so we're measuring a little bit less here in gravity, and here we're measuring a a little bit more. So that's why you have the discrepancy of 9.78 at the equator and 9.83 at the pole, both due to the rotation of the Earth. And again, two reasons. One of them is that the Earth is not a perfect sphere, it's somewhat oblate. And the other one is that the tangential speed, as I explained, means that some of the gravity needs to be taken up to supply the centripetal force toward the Earth's center. And that then comes out to, well, subtract just a little bit from the 9.83 and we get 9.78 here. We get 9.80 in the lower 48. I know from my German textbooks we get 9.81 in Germany. We get 9.82 in Alaska. I measure that all the time in the lab. And here I don't measure it, but it would be 9.83 at the pole. And of course with several experiments you can measure that and you do get different accelerations due to gravity around the world, depending on where you are, what latitude, and again, it's caused by the rotation of the Earth.